So welcome everyone to this tutorial on large language models. So we will be using this model called Crystal LLM to understand how generative models work in material science and how generative models like large language models can be used for crystal structure prediction problem. Okay, so before diving into this package of Crystal LLM and before generating, we will do a small recap of what an LLM actually is. Okay, and how this package actually works, and then we will generate some structures and see how the generation process works. So LLMs, think of LLM as a given a initial token, an LLM is trained such that it can predict the next possible token. Okay, so suppose you have a sentence, and in a sentence you can think each word as a token. Okay, so that's one easy abstraction of a token, but depending on the field you are on, you can have different definitions of a token is. For our understanding, each word, each space, each punctuation is a token. That is sufficient. Okay, so suppose this is my first token. I give this as an input to the LLM. It will give me the next most probable token that it thinks is the correct one based on the corpus of texts that it was trained on. Okay, so now that I have got my second token, how do I generate my next token? I will tag this new token with my old token, and these two tokens I will then push to the LLM and generate the third token. Once that is generated, it is then tagged on, and now I have a bigger list of tokens. So I have the first three tokens, and that will uh, predict the next token. So it's like every prediction takes into account all of the previous tokens. Okay, so this is the context. So this is what sets the context for this one, the next token. Okay, so this context thing is learned by that attention mechanism that you have already seen in class. Okay, now what happens is inside this LLM, that given a token, given this token, when this goes inside the LLM, uh, it outputs a list of probabilities for of the possible words that it can think of. Okay, that should come next. Like for example, here it should be I have a dream, I have a dog, I have a question, I have a plan, I have a problem, I have a car. So you can have multiple possibilities. Based on the text it was trained on, this LLM thinks that I have a dream is the most probable sentence. This dream is the most probable word. Okay, so it outputs probabilities of words that it thinks are possible, and based on these probabilities the next word is selected. So the most basic scheme of selection would be just select the most probable word. Okay, and in this way, by recursively acting, this LLM can generate a whole sentences of coherent text. Okay, so this package Crystal LLM, what does it do is it generates crystal structure by generating CIF files. So CIF files are crystallographic information files. So this is how a CIF file looks like. A CIF file specifies the crystal structure completely for any compound. So say we have this CIF file for NaCl. Okay, so a CIF file starts with this particular line. So your first word will be data underscore whatever the compound the CIF file corresponds to. The next line is the symmetry space group. So you have the symmetry space group name, HM stands for Hermann-Mogben symbol, and you have the space group symbol P1. Next you have the cell vectors A, B, C, the cell angles alpha, beta, gamma. The place of this space group notation in the international tables, the formula, the cell volume and number of formula units you have in the cell. And after this, what you have is this atom site, like what is the element in this atom site, the site label, like this is chlorine 1, chlorine 2 or chlorine 0, it starts from 0. Then you have the site occupancy, and then you have the fractional coordinates of x, y, z and the site occupancy. Now once you have a CIF file, the Crystal LLM is trained on a large corpus of CIF files. So they give CIF files, they tokenize this CIF file. So this is a token. So this is how you tokenize it. So you like break down each word or each space into smaller chunks. Okay, that goes as input, and given a chunk, you want to predict what will be the next chunk. So while training, the LLM is given some parts of the SIF and it has to complete the SIF, and based on its completion, like we know the actual SIF, that the actual target that we want to achieve, and based on this we can define the cross entropy loss, and once you define that loss you can actually change the weights and biases in subsequent back propagation steps, and that's how you like make this model learn how to generate coherent SIF files. Okay. So this is how generation happens in this Crystal LM package. Now once you have a generation, okay, so there are some plausibility checks that you need to do. So first is for after a structure is generated by this LLM, SIF syntax and space group consistency are checked. So if your space group is P1, what it checks is, does that P1 symbol matches with all the atomic positions, and does the atomic positions actually correspond to the P1 symbol. So that's a space group check. If the SIF syntax is wrong, then this generation is targeted as invalid. So you just check that all the syntaxes are correct. Okay. You check bond length. So atoms cannot overlap, also they cannot be too far away so that there is no bonding. So there is some realistic range within which a bonds must fall. Okay. And and then there is multiplicity and site occupancy. So it's like checking the consistency within the SIF file itself. Okay. Lattice parameters for compounds can lie within certain ranges only, it cannot be infinitely large. Okay. So such checks on geometries are actually done to avoid any unrealistic generation. Okay. But the thing is, none of these checks encode any physics in them. Like we haven't tested how feasible or how thermodynamically feasible is the generated structure. So far we have not done anything to check the physical plausibility of any generated structure. So herein comes the Monte Carlo tree search, okay, where we will see how feasible is a generated structure based on the formation energy. Okay, so we have this crystal LLM which will generate a structure, and we have another graph neural network which can predict the formation energy of a structure given the crystal structure. Okay, and formation energy is an indicator of the stability. So lower the formation energies, you can expect that material to be stable and forming. Positive formation energy materials are not expected to form. Okay, so now let's take a look at this Monte Carlo tree search algorithm. So you start with a node, so which is the compound. Okay, so it's KBr in this case, and once you have decided the compound, from in any subsequent steps would have multiple possibilities. Okay, so your space group for this KBr compound can be P3M1, FM3 bar M, or I4 by MMM. Okay, and each of these paths will have different probabilities. So suppose you select one of the paths with the highest probability, and then the next thing that next decision point that you subsequently come to would be the cell length. So you have this cell length A. Now this cell length can have many possible values. So you can go through this path 1, path 2, or path 3. Suppose you go to this path 3. Okay, and then subsequently again for cell length B you can have multiple decisions. So suppose you take this 3 path and continue with the whole SIF generation process. Okay, and now that you have a complete SIF, you use this one to evaluate the formation energy. Okay, and once you have ranked the formation energy, once you have got the formation energies, you can do this exercise for multiple branches from every time it has a multiple nodes to come up with. Okay, so it's like this is a child node, and from the tree node, so you will explore each of the child node. Okay, and finally complete the completion process of the CIF and evaluate the formation energies, and based on the formation energies you will rank each path. Okay, that which path seems promising. And once you have done that for lots of number of repetitions, based on the scoring of each branch, what you will see is there are some branches which look much more promising in terms of giving a good formation energies than other branches. So and during all this process, your main backbone LLM model is actually not being tuned, the weights and biases are not changing. So this backpropagation process is not the neural network backpropagation process that we saw where the weights and biases would get changed. Okay, this backpropagation is backpropagation of the score that you computed and identify which of the branches are actually promising for this generation process. So after having multiple iterations of this Monte Carlo tree search, what you actually get are compounds which are energetically very feasible and are very probable to form. Okay, so this MCTS algorithm will help you explore many of the branches which is not possible by a single generation routine. Okay, I mean, think of this: every time you have a branch, and if your algorithm all it does is select the most probable branch, then every time you give KBR, you will always end up in P3 M1, this space group which seems the most probable to the model. Okay, but the other least probables, other least probable space group can give rise to other polymorphs of this same compound, which may not exist in the training literature, so it did not think them as probable. But once you do the complete generation, your formation energy predictor might show that that path is also equally promising, and you may have discovered a new polymorph of that compound which you never knew had existed before. Okay, so it balances exploration and exploitation, and going or exploring multiple branches mean that you will not always collapse to some trivial or repetitive token patterns if you start with the same thing. So as I said, you start with KBR, it's not necessary that you will always end up in this P3 M1 branch. Okay, you may end up here or here depending on how your evaluation of this whole tree went. Okay, and and also you are using a search algorithm to generate new structures from the same input rather than changing the model itself. So that's also something very important about this algorithm. You are not changing the core baseline model. Given a model, you are trying to see what are the possible paths I can explore based on the model outputs. Okay, so this completes the explanation for this package. So now let's try to run this package. So once you have downloaded the files, go inside that folder, you will find this CrystalLM notebook. Okay, so we will just check the path. So this is the path, and inside the notebook, if you go, you will see all these files that are inside the folder, CrystalLM folder. And now what you need to do is add CrystalLM to your Python path. So execute this cell, and the paths will be updated. Okay, in this tutorial, what we will do is we will download a small 25 parameters model and try to demonstrate generate structures from using that one. So these tutorials are unlike your previous tutorials where you defined a model from scratch, trained it, and then did evaluation. So these language models are actually very large models, and training them is not possible in a short time scope and in desktop like machines. You need large compute clusters for that. So what we will do is only do inference. So we will just download the model, load the model, and do inference with that model. For in this case, inference is generation. We will just do generation with that model. So you run this block, and the small model is actually downloaded. So you can visit the GitHub repo of CrystalLM, and you can see they have listed a large number of models that they have particularly trained. So you are selecting one of the models here. Okay, so now once you have downloaded the model, next what you need to do is generate a prompt. Okay, and there is a Python file that make the prompt, and the prompt is I want to generate LIMNO2. And what this Python file does is it will write data underscore LIMNO2 in this text file called myprompt.txt. Okay, because all zip files start with the word data underscore whatever the compound you want to generate, as we already saw here. Okay, so now you have a generated prompt. Now what we will do is we will run the model, and there are some generation parameters that are actually given in the model. So let's try to see. So you define the output directory, you define the starting point, which is the prompt file that we just created, myprompt.txt. We want to generate 3 samples. Okay, and top K10. I'm coming to this. Okay, so this is selection of the next token. What's the strategy for the selection of the next token? And we will use device CPU, and max 3000 tokens it will generate. So either shift terminating conditions is reached first, or 3000 tokens, whichever is reached first, the model will terminate there. Okay, and now for this top K10 parameter. Okay, let's try to see this. Every time a token goes into an LLM, you have a list of probability outputs. The simplest strategy is to use the most probable output. But every time you do that, for the same starting points, you will always collapse into the same outputs for the rest of the generation. And in order to introduce some randomness into this generation process, so that you can explore new chemical spaces and lattice structures and everything, one of the strategies to do is top K10 sampling. So you take the top K entries. Okay, for our case is K equals to 10. We will take the top 10 entries, and for the next token, what it will do is not predict the most probable one, but predict randomly out of the top 10 ones, anything out of the top 10 ones. Okay, so this is again an type of exploration strategy, so that you can explore new spaces. So out of it will randomly select any of the 10 tokens, any of the top 10 most probable tokens. Okay, so that's a correct way to put it. And now if you run this block, what you will do is you will see this running for some time on your CPU, and it will generate the sample structures, sample 1, sample 2 and sample 3, because I had given 3 samples to generate. Now you can visualize these structures that you have generated using ASE, atomic simulation environment. And I want to visualize sample 2 SIF, and I want to visualize a supercell of that SIF. And if I run this, you can see a SIF, and it's an interactive environment. You can rotate and see it. So that's what it generated. Okay, and once you have the generated SIFs, you can actually store them as SIF files, save them as SIF files, and later use this SIF as inputs to other GNN models for doing any kinds of property prediction or formation energy prediction, like the one we did with transfer learning in Align. Okay, so that's a very nice exercise to be done, that you generate structures here and using this generative model, and use other neural network models like Align to predict properties of this generated files. So that brings us to the end of this tutorial on Crystal LLM. We will see you on the next tutorial. Thank you.